Okay, welcome back. We are on sugars again today. On sugar. That sounds like my kids. Um, there's no mic up here, so I will just endeavor to talk loudly. If you can't hear me, tell me to speak up. So when we last talked, we were talking about the name beta D glucopyranose, and we were examining the features of this structure, which is, as we pointed out, a cyclic hemiacetal. Yes, it's behind my laptop. Ta-da! I'm really good at paying attention to stuff. Sorry. Okay. There we go. All right. So this is the structure of beta D-glucopyranose. It's easy to remember because you just draw a chair with the oxygen in the upper right corner, and then you put the rest of the groups in at equatorial positions. This is a 6-carbon sugar. 1, 2, 3, 4, 5, 6. And as we pointed out, it's a cyclic hemiacetal, and you can tell that by looking at carbon 1, which is attached to 2 oxygens. One's an alcohol and the other's an OH group. And so that's a hemiacetal, and we call the carbon associated with that hemiacetal the anomeric carbon. And this cyclic hemiacetal linkage is part of the sort of described by the name pyran in this long extended name. Pyran refers to a 6-membered ring containing oxygen. This would not be a 6-membered ring containing oxygen if it were not a cyclic hemiacetal. I will point out that this structure, I think as I did last time, is in equilibrium with an open chain aldehyde form. And in its open chain form, this is just called D-glucose. So the pyran refers to cyclic, and then we'll talk about what gluco, beta, and D refer to. So beta refers to the stereochemistry of the OH group on carbon 1, or on the anomeric carbon. If it's up, it's beta, and if it's down, it's alpha. So there is another form of glucose that's also in equilibrium with beta D-glucopyranose and its open chain aldehyde form, and that is the form where the OH group on carbon 1 is down. And we'll call that alpha D-glucopyranose. And you can see that it's possible to interconvert these forms simply by rotating around this bond between carbons 1 and 2, such that when you form the cyclic hemiacetal, this oxygen attacks the carbon, and the carbonyl oxygen's down here. Okay? So this is one of the few times in stereochemistry where it's possible to interchange stereoisomers simply by opening up a ring and then rotating around a bond. So these two stereoisomers are in equilibrium with each other. They differ at one stereocenter, so the relationship between these two is that they are diastereomers. Diastereomers have different chemical and physical properties, and they're a particular kind of diastereomer because they differ at only one stereocenter. And when that is true, they can be called epimers. That is a term we use for diastereomers that differ in configuration at one but not all stereocenters. At one and only one stereocenter. And then because this stereocenter is the anomeric carbon, we will use another term to describe these isomers, and that is anomers. They are epimers at the anomeric carbon. So people will call this one the beta anomer, and they'll call this one the alpha anomer. And when you have glucose in solution, it is a mixture of these two. And the process of converting one to the other through the open chain intermediate is called mutarotation, because it's not actually a real rotation. It looks like you've done some rotating, but you actually have to open the chain first to exchange the two positions, to exchange the OH from here to down there. Okay, so that's what beta and alpha mean, and the pyran refers to the six-membered ring cyclic hemiacetal form. Questions so far? Yes? I'll tell you that. Yep, stay tuned, we're coming. D refers to the stereochemistry at carbon 5. So, yeah, D is carbon 5 stereochemistry, and if it's up, it's D. If it's down, it's L. Those are two archaic forms of naming stereoisomers. With amino acids, we talked about L amino acids versus D. We have a similar system for sugars. It actually has nothing to do with whether or not the sugar rotates light in a left-handed versus right-handed direction. So that's confusing. And you can't assign it in an absolute sense. It's always by analogy to a particular isomer of glyceraldehyde or something like that. So it's not particularly important, but when it says D, the group on carbon 5 is up. And most sugars in biology are D sugars, in the same way that most amino acids in biology are L amino acids. Okay. The gluco portion refers to stereochemistry at 2, 3, and 4. Okay, so if, starting with 2, if the stereochemistry is down, then up, then down again, we'll use gluco. If it's up, up, down, we'll use mano. And if it's down, up, up, we'll use galacto. Now there are other combinations, but these are the three that are most important in biology, so those are the ones we'll worry about. Your text provides a lovely list of all 6 carbon sugars in their various names, but as I said, only 3 of them are found a lot in biology, so those are the ones we're going to pay attention to. For glucose, it's easy because all of the OHs are equatorial. For mannose, as an example, I can just draw the smaller structure of mannose here. It's going to be exactly the same if I were to do beta D mannopyranose. It's going to be exactly the same as glucose at carbon 1 and at carbon 5. And then at carbons 2, 3, and 4, it's going to be up, then up, and then down, whereas in galactose, it will be just like glucose until you get to carbon 4, when the OH group will be up. Okay, so you're going to need to know those ways of talking about sugars. You're going to need to know the difference between glucose, mannose, and galactose. You're going to need to know the difference between alpha and beta anomers. Okay, questions so far? Now, there are going to be other ways of drawing these things that you will encounter in your future. The problem is that I hate them because they're a little bit more difficult to understand. So I'm not going to require you to learn these, but I'm going to say just a few things about them so that in the future, someday, if you encounter these forms, you can come back to your notes and realize what on earth they're talking about. So if we take this, what's the best way to do this? If we take this 6-membered ring sugar and we say, and we imagine that we've forgotten everything we know about organic chemistry and we're scared of drawing chairs, then we will simply draw a hexagon with an oxygen here, and then again, forgetting everything we know about organic chemistry and sp3 hybridized carbons, we'll draw each group on carbons 1, 2, 3, and 4 either straight up or straight down. So in the beta anomer, OH is here, hydrogen is there, OH is here, hydrogen's here, OH is there, hydrogen's there, OH is there, hydrogen's there, and then the CH2OH group is there. And in fact, this is where, this is the frustrating to no end. We'll actually draw CH2OH. So that's how people will sometimes draw 6-membered ring sugars. You will see that potentially in your biochem text. And if you do, notice that it's not pretending to tell you anything about the actual shape of glucose. It's mostly just a way of showing you that it's a 6-membered ring and showing you the stereochemistry. This is the so-called Hayworth projection. Now, it gets worse because people will then, because they are scared of drawing 6-membered rings, will instead open up the ring to get a new kind of shape. So here's the OH on carbon 5, 4, 3, 2, 1. Carbon 1 is an aldehyde, which they will write like this. And then we're going to put still OHs here, here, and there. Okay, see what we did? We just opened up the ring. You okay? I got to make sure I do this right because I've never really bothered to learn how to do it because I hate it. All right, so then we're going to straighten out the chain, and we're going to keep the aldehyde here, but we're going to pull this OH group out in this direction. Okay, so and actually, before we do that, we're going to make our lives easier. Well, somebody's life easier. To see this, actually, we're going to need to use this particular form. So what we've drawn here is conceptually equivalent to what we drew here. The CH is down, and this bond is going back away from you in the page. We're going to need to rotate around this bond because we want the CH2 group to be over here. And so if we do that, if we rotate it so the CH2 is in this direction, that's rotating around this bond, and now I've got to think for a minute. Yeah, that will cause us to have, and I think I'm doing this right, that will cause the CH2OH group to be here, and that'll cause the OH group to be down and the methyl to be there, or the hydrogen to be there. And again, to reassure you, I'm not going to ask you to draw sugars this way, but I do want you to know sort of where it comes from. So we could modify our drawing here to say if we put the CH2OH group here, then the hydrogen should be up and the OH group should be down. All right? So now we're going to straighten out the chain. We're going to put the aldehyde here, and then at the neighboring carbon, OH is down and hydrogen is up. At the neighboring carbon, OH is up, hydrogen is down. At the neighboring carbon, let's see, OH is down and hydrogen's up. And then at the carbon at the end, hydrogen's up and OH is down. And then you have the CH2OH group. Yuck, right? Already you're losing all the sort of three-dimensional structure of this molecule. And then, then we're going to rotate it and draw it like this, with the aldehyde up at the top, the CH2OH at the bottom, and then we've just got to put the hydrogens and the OH groups in the right place. OH here, 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 OH there. And if you go look in your text, this is the structure of D-glucose, and this is its so-called Fischer projection. Again, hate it, but you will see it. So, yeah, go ahead. If you mirror it, is it the same thing? Yeah, and the answer is no, but you wouldn't know that if you don't know sort of the rules, because there is stereochemistry here. What this really means, because think of it this way, if you made the mirror of this, you'd have the enantiomer of glucose, right? So if you made the mirror of this Fischer projection, similarly, it would be the enantiomer of glucose. And your text tries to be helpful and tells you, actually, from this perspective, I always have to look it up because I never bothered to learn it. No help there. Well, somebody needs to look it up. I think the bonds that are up and down are all considered as though they were going away from you. And the bonds that are left and right are considered as though they were coming out at you. So you're sort of looking down on an sp3 hybridized carbon from a strange perspective. And if you want to figure out how to do that, you can make a model. But basically, when you draw the Fischer projection, you're really communicating this kind of structure. And so, yeah, if you drew the mirror image and set it back down, you'd have the enantiomer of it. All right, so I don't know why the air quotes are in the wrong spot there. Well, they're not air quotes when you write them down, though, are they? Right. So this is the Fisher projection. Now, one advantage of the Fisher projection is it can be easier to see some of these stereochemical relationships. For example, the D isomer always has the OH group on the right side. And then it's also easier to see the differences between glucose and mannose and galactose when you sort of draw it this way. But again, this is not the biologically relevant form of glucose in the sense that most glucose in solution is in its cyclic hemiacetal form. There's only a small amount of the open chain aldehyde. We'll use that open chain form for chemistry, but it's always an intermediate, never the end point. All right, so I am sorry that people in your future may draw sugars like this or like this, but you will know when they do, you will say to yourself, I know what they're really talking about, and you'll feel smart because you know more than the folks that are telling you about the sugar structure. Okay, questions so far? All right. So I want to talk about carbohydrate chemistry, but then also some carbohydrate biology. And I want to start by talking about these beta and alpha anomers. I told you they were in equilibrium. So, oops. So I'm just going to redraw them. Here's going to be the beta anomer, and here is the alpha anomer. And what I'm going to tell you here I don't think is discussed in any detail in your text. But it's a useful principle. It's a useful demonstration of some organic chemistry principles. Here's the OH group. All right, alpha and beta anomers. Now, if you mix, present in aqueous solution, we observe about a 67% amount of the beta anomer versus about 33% of the alpha anomer. Now, you may first look at that and say, hey, that makes sense because I know that it's less stable for groups on a ring, a six-membered ring, to be axial versus equatorial, and the reason for that is sterics, right? If you're axial, you have potential clashes with the other axial substituents. That's 351 stuff, right? One thing you may or may not have learned in 351 is that there are some tabulated A values that tell you how bad it is to have a group axial versus equatorial. Does that sound familiar? Have you heard about that before? No, you got nothing. Okay, that's all right. The A value tells you in kilocalories per mole how bad it is to have a group axial versus equatorial on a cyclohexane ring. So for the OH group, the A value is plus 1 kilocalorie per mole, meaning that if you had a cyclohexane ring, the conformation where the OH group was axial would be 1 kilocalorie per mole less stable than a conformation where it was equatorial. Now, through some Gen Chem math, which you don't actually have to do, but I will do for you, based on that number, we can calculate what the equilibrium constant should be by taking the number E raised to the power of minus delta G over RT. So plug in the numbers that apply at room temperature, and you come up with the expectation based on A values that actually we would have expected 75% beta anomer versus 25% alpha anomer if sterics were the only thing that was going on. All right? What this tells you is we observe more of the alpha anomer than expected. Which must mean that the alpha anomer is more stable than expected. So there's something other than sterics going on. Now, a great rule of thumb in organic chemistry is if sterics doesn't explain something, you start looking for explanations involving electrons and orbitals. The rule of thumb that chemists say is, well, if it's not sterics, it's electronics. And so let's zoom in on the alpha anomer and let's imagine what's going on there that might not be going on in the beta anomer. And this will be maybe difficult for some of you to see if you haven't been exposed to a concept called hyperconjugation before. And we're not going to spend a lot of time on it, but it's interesting to think about here. Hyperconjugation is when a filled orbital overlaps, filled orb, that sounds kind of mysterious. Filled orbital overlaps with an adjacent empty orbital in the same molecule. And that allows the electrons in the filled orbital to spread out, and that is always a stabilizing effect. Okay, looks like it's maybe going to work. So hyperconjugation is when a filled orbital overlaps with an adjacent empty orbital in the same molecule, and it is a stabilizing effect because it involves electron delocalization. The electrons in the filled orbital spread out and therefore move down in energy. All right? And you don't need to worry about this concept in a huge way. There are two lone pairs on this adjacent oxygen, and one of them is in an orbital that looks kind of like this. And we'll use color, as we've done before, for wave function signs. So this is a lone pair. It's a non-bonding orbital. It's the filled atomic orbital on oxygen. And then on the adjacent atom, we're going to draw the carbon-oxygen sigma star. This is the antibonding orbital. You may not have drawn antibonding orbitals before, so what I'm going to draw now may seem a little bit unusual to you. But this is what a sigma star antibonding orbital looks like. An antibonding orbital is made every time you make a bonding orbital, and the antibonding orbital is empty. And so you can think of an antibonding orbital as the place where electrons would go if you had more of them. But in any case, when we have the alpha anomer, this is the sigma star, the antibonding orbital associated with this carbon-oxygen bond, and it is empty. When you have the alpha anomer, the sigma star is pointing in the right direction for electrons on the oxygen to spread out a little bit into that sigma star. Okay? So the key concept here is that in the alpha anomer, the lone pairs on the ring oxygen get to delocalize a little bit, and that's stabilizing. In the beta anomer, the geometry doesn't work out quite as well. Because in the beta anomer, the OH bond is pointed in a different direction. We can still draw the sigma star associated with that OH bond, but it's no longer going to overlap well with this lone pair that's on oxygen. Again, one of the interesting features of an antibonding orbital is that it has a node in between the two atoms, so that if you filled it, it would tend to pull the two atoms apart. But you can see that now if we were to look down this carbon-oxygen bond, we would see that the lone pair is basically perpendicular to the sigma star. And when the lone pair is perpendicular to the sigma star, there is no interaction and therefore no delocalization. So there is this thing called hyperconjugation that makes the alpha anomer more stable than expected. Go ahead. What about the other lone pair? Does it line up? That's a good question. And if you draw it like this, you could imagine it doing so, though it's mostly going to line up with this space in between the two nuclei that's a node. If you look up above, the beauty of the alpha anomer is the lone pair can overlap with just one lobe of the sigma star that's projecting back away. And one thing you may not know is for two orbitals to interact, they have to have the same wave function sign, otherwise it's not favorable. So overlap with the same wave function sign, is good and stabilizing. Overlap of this one, whatever its sign, with these two that are opposite in sign of each other will just sort of be a cancel out kind of interaction. So I understand this may be troubling for some of you, and I'm really not going to push you on it, but I want you to have heard about it. The alpha anomer is unexpectedly stable, and this thing, this observation is called the anomeric effect. And there's a lot more we could say about it, but I think that's probably enough. All right, other questions? Yeah.
Do we ever see interaction between the hydrogen on the carbon in the OH group and the oxygen in the room?
So would you see hyperconjugation between this oxygen and the
oxygen in the OH group on the 6th carbon?
Oh.
With the oxygen.
Oh, do you ever see hydrogen bonding? Possibly. Sugars, because of their OH groups, are very soluble in water. So I suppose you could look at the crystal structure of glucose to see if there is such an intramolecular hydrogen bond there. That would be a 1, 2, 3, 4, 5-membered ring, so it sounds reasonable. In water, that kind of thing is likely inconsequential because there are so many other water molecules that it could hydrogen bond with. It's probably not any more favorable to do the intramolecular hydrogen bond than to hydrogen bond with water. All right, others? My son's in general chemistry and texted me yesterday and asked, Dad, is a hydrogen in one water molecule interacting with the oxygen in another water molecule a hydrogen bond or a dipole-dipole interaction? And I said, well, to get the question right, to get the question right, you probably want to call it a hydrogen bond, but hydrogen bond is a type of dipole-dipole interaction, right? Which you now know, but you can remember fretting over such things when you were younger and less experienced. Okay. Fortunately, unlike many of you, he will not need to take organic chemistry, so that works out nicely for him. Okay, so those are individual sugars. Now I want to talk about glycosides. Glycosides are just sugar acetals. The simplest glycoside would be if we took, say, glucose, And sometimes, just as a point, sometimes people, you have to sort of be careful when talking about sugar structure, because if you draw one anomer, if you draw stereochemistry at the anomeric carbon, you mean that you only have that anomer. And at least with glucose as it is, there's no way to just have the one anomer. I suppose you could purify it away, but as soon as you put it in water, you'd have the equilibrium again. So when people want to when people want to say, I have the cyclic form of glucose, it's D-glucopyranose, but I have both alpha and beta anomers, they will use the squiggly line to indicate both stereochemistries at that anomeric carbon. So you'll see that, and when you do, don't worry about it. Just know that it means there's both anomers present. It's a mixture of diastereomers. All right. So if you use an alcohol with catalytic acid, you know, we've used toluene sulfonic acid before, but it could be something else. When you do this, you will replace the OH group on the anomeric carbon with a methoxy group from the alcohol. Now, I know that looks weird and different to you, but that's only because of the distracting six-membered ring. In reality, you have seen something like this before many times. You start with a hemiacetal, and then you use another equivalent of alcohol and a catalytic acid, and then you make the full-on acetal, right? So the question is, can you see the connection between what we have done before early in the semester, hemiacetal to acetal? Can you see that connection with what we did up here? It will seem obvious now that I've pointed out to you. It will not seem obvious to you on the exam. You'll look at that and you'll say, you will be distracted by all the OH groups, distracted by the six-membered ring, and you'll say, what in the heck is going on? And then you'll start guessing things, and that never goes well, right? So, see the connection between this. See that carbon 1 is bonded to two oxygens, another carbon, and then a hydrogen that's implied and not shown. Now, if we were to do hemiacetal formation, oh my goodness, why didn't somebody stop me there? Yeah. Okay, if we were to do hemiacetal formation in this simplified sense, what we would have done is first used our catalytic acid to protonate the OH group to turn it into a good leaving group. I hear whispering. Am I doing something stupid? No? Okay. I'm just paranoid. That was an extremely paranoid thing to say. I'm really sorry. So you would protonate the OH group to turn it into a good leaving group. Then electrons on the oxygen would kick down and water would leave. You get this oxonium ion. And then a second equivalent of alcohol is going to come in and attack the carbonyl carbon. You will then get this intermediate in which the new OR group that you put on the acetal carbon is still protonated, and then some base comes along, probably the conjugate base of our acid, removes the proton, and then you get the acetal. So the challenge for you, whoa, that's not an equilibrium arrow. The challenge for you is to draw the mechanism here based on the mechanism below. I'm not going to do that because I want you to do it, because doing so is going to help you see the connection between what we've seen before. Now, the methoxy group is boring. And so there are a lot more interesting acetals that we can make with sugars. One of the questions we could ask is, what if the alcohol that comes in and replaces the OH group on glucose is another sugar? All right? So let's try that. Let's draw the beta anomer of glucose, but instead of having an OH group at carbon 1, what we're going to do is have carbon 1 be attached to the OH group from carbon 4 of another glucose molecule. Okay. Now again, you will be tempted to look at that and be scared, but pay attention to the functional groups you know. Here is an anomeric carbon that's bonded not to two OH groups or to one OR group and another OH group, but rather it's bonded to two OR groups. This is an acetal. But when the anomeric carbon is on a sugar, we call it a glycoside. And this linkage between carbon 1 and carbon 2, or 4 on the other sugar, we're going to call that a glycosidic linkage. You will hear that definitely in biochemistry. Now, you may be looking at that and saying, wow, who picked that the OH group on carbon 4 was going to form an acetal with the anomeric carbon 1 on another sugar? But before we talk about that, do you guys see how we can get this from two different glucose molecules? If you were to try to draw a mechanism of this, you would need to show taking one glucose molecule and getting it to the oxonium ion stage. And then at that stage, you would use the OH group on carbon 4 of the other glucose to come in as the alcohol and be the nucleophile. Okay. Why did I draw that there? That's weird. Okay. Now, you may ask, how did we choose for the group on carbon 4 to make this bond instead of any of the other OH groups on the sugar? And the answer is two possible answers. Number one is enzymes, and number two is an elaborate scheme of protecting groups. And if you want to know more about that, the Savage Lab is world-class experts on sugar chemistry, and you basically have to protect the other OH groups that you don't want to interfere in the process so that you can do the chemistry that you want to do. Now, this glycosidic linkage is a linkage between carbon 1 on one sugar and carbon 4 on the other. The arrow indicates that carbon 1 is the anomeric or acetal carbon, and that the OH group from carbon 4 of the other sugar is the alcohol. Then we'll use the term beta to describe the fact that the OH group at carbon 1 is up. So this is a beta 1,4 glycosidic linkage. And this makes a difference. This molecule has a common sort of non-systematic name. It's called cellobiose, and it's a subunit of bacterial cell wall carbohydrates. It's a subunit of fiber. So this is a carbohydrate that surrounds us, but in nature, in plants and so on, but we don't digest it. Now, if you change that linkage keep the two sugars basically the same, but then change the stereochemistry of the linkage so that now carbon 1 on one molecule of glucose is down. It's the alpha anomer. And then that carbon 1 will be attached to an OH group from carbon 4 on another molecule of glucose. We're going to call this an alpha 1,4 glycosidic linkage. And this structure, instead of being cellobiose, this is maltose. And this is a component of starch. You can get it from various starchy sources. So if you... What did I do? Okay, well, nobody's going to tell me. Okay. Paranoid again, what the heck? So if you're eating a saltine cracker and sucking on it in a gross way like a small child and it starts to taste sweet, you are tasting this. And notice that it's just stereochemistry that makes the difference between the two. Yeah? Are there molecules that will alternate between alpha and beta? Not generally in a linear fashion like that. There are other complicated carbohydrates that have both types of linkages, but yeah. Yeah. All right, we'll stop there and we'll do a little bit more with sugars next time, then move on to lipids.